Okay, hello everyone. We are starting section 3.3 on partitions, and the homework, I'll state the homework at the end. I just want to get started because I'm going to do 20 minutes. I'm really going to try not to go over 20 minutes. I'm going to stop 10 minutes wherever I end at 10 minutes here and then do another 10-minute video, and then we'll be done with this section. So this section deals with partitions, and we're going to start off with the definition. So of course, first, if you want to pause the video and then come back to it when we go over this, that would be great. All right, so definition we have of a partition is the following. First, you're going to let A be a non-empty set, and P, which it looks like the power set notation, and in math, certain notations are the same, but depending upon the context, you should know which definition you're using and what subject you're talking about. So in this case, we're talking about a partition. So P is a partition of A if and only if P is a set of subsets of A such that these three conditions hold. So this is the definition. And as you all know, it's really important to understand the definition. So first, if you have a set X, if X belongs to a partition, then X cannot be the empty set. So it's definitely not an empty set. That's one of the first condition. The second condition is if X belongs to a partition and Y belongs to a partition, then either X equals Y, so the sets are equal, or X intersect Y is equals the empty set, so they're disjoint. And we sort of talked about something along these lines. You might remember that we'll talk about a little later in the video that we had something else was similar to the fact that if certain things happen, they're either equal or disjoint. Okay, and the third condition is when you take the unions of all the X's for X belonging to the partition, it equals the set A. Okay, so let's look at an example, and this is in your book, and this is figure 3.31 in your book on page 158. So you can just sort of make a note of that in your notes. And we have here, this is a really nice example of partitions. When I talk about partitions, I usually talk about at a banquet hall. You know how there's a big banquet hall and there might be several events going on at the same time. So you'll have dividers to section the rooms off. That's another way to look at partitions. And so let's just make sure we understand the definition of partition by this example. So this entire set, we're going to call set W, is going to be all employees in a work area. Okay, so this is a set of all employees in a work area. And again, and understand that the definition, every cubicle contains at least one worker. And so we see here we have at least one worker. Here we actually have two workers. Here we have one worker, I'm sorry. And here we have two workers. And if we want, we can actually call this workstation 1, workstation 2, workstation 3, and workstation 4. Okay. And so that first condition is met because every cubicle contains at least one worker. There's not a W sub 1 or 2 or 3 or 4 that doesn't have any workers in it. So it's not equal to the empty set. That's what that first condition means. So we satisfy that first condition. The second condition says that, if no worker is assigned to two different cubicles in this example. So we have two workers in workstation 2, for example, and we don't see any overlaps basically. And then 3, every worker must be in some cubicle. So we've actually formed a partition of W. So if we notice that W equals W sub 1 union W sub 2 union W sub 3 union W sub 4. Okay, and so that's the definition of a partition. Let's look at a couple more examples. So I'm going to pause the video and write down the examples, and then we'll go over them. Okay, so in example 2, we have P, the power set equals DE, where D is the set of odd integers and E is the set of even integers. So this represents a partition of the integers. Okay, and so you can think about that for a minute and think about those three conditions and how it meets those three conditions. Now, example 3, two other partitions of Z are, if we had, so dot, 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 the set containing -2, the set containing -1, the set containing 0, the set containing 1, and so on. That's a partition, and the set containing the integers, so the entire set. So the first one, if you think about it, is talking about each element is a partition of itself, because if you look at the set of each element, when you take the union of those sets, it's non-empty, it's equal or disjoint, and when you take the union, it actually equals the set of integers, just like if you had one big partition. Okay, so this is just like if you had the first case right here is where if you had a banquet hall and say you had 20, I don't know, for some reason 20 people wanted an event for themselves, and so you would partition off into 20 different partitions and of one person. That's what this first one is saying. So it's a party of one. Okay. And then the second one is saying now everybody's invited to the party, so we're just opening all the partitions up, and that's also a partition. Okay. Now this nice fact and theorem. So again, you can pause the video and then press play to play it again as I go over this fact and theorem. And I'm going to go over rather quickly because I'm not going to prove this theorem. I want you to look in the book and see how they prove it. But the first fact goes with the last example. For any non-empty set A, the family, so the set containing, and I have an extra bracket in there, the set containing the set of X such that X belongs to A, that's a partition. So that's that first example on that last page. And the set containing A, the entire set A, are partitions of A. So that's example 3. So I want to make sure. So, see example 3 for this above fact. Okay. Now this next theorem, theorem 3.31, is one that's useful to us. So this says if R is an equivalence relation on a non-empty set A, and you all know what an equivalence relation is, what properties it holds, then A mod R, the set of equivalence classes, remember that's the set of the equivalence classes for R, that is a partition of A. So this is what I was talking about from that definition. You might remember in terms of equivalence classes are either equal or disjoint. So if you have an equivalence class, and so keep this in mind for your homework, if you have an equivalence class, say 0 mod something, 0 mod R, and it equals one element, and then you have 2 mod R, and that equals the same element in 0 mod R, then those two equivalence classes must be equal, because equivalence classes are either equal or disjoint. So this theorem is stating that you have the equivalence classes. If R is an equivalence relation on a non-empty set A, then A mod R, the set of equivalence classes, is a partition of A. Okay, and so I want you to actually look at this theorem. I want you to look at the proof in the book of this theorem to see if you can follow along and see how they actually discuss the proof. Okay, so let's look at example 4 and look at an example of what we were talking about in that above theorem. So let A equal the set, sorry, my brackets are looking funny with the stylus, 4, 5, 6, and 7. That's a set. That's not good. Okay, let A equal 4, 5, 6, 7, and let T be an equivalence relation, or be the equivalence relation. And I'm going to pause so I can write this down, and then you write it. Okay, so I might go a little over. I said I was going to do 10 and 10, but I really want to just finish this example because I don't have too far to go in the video after this, on the next video. So if A is equal to 4, 5, 6, 7, and let T be the equivalence relation given by the set containing 4, 4. So 4 relates 4, 4T4, 5T5, 6T6, 7T7, 5T7, 7T5, 7T6, 6t7. And I'm saying t as the relation t, not 67. So I don't want to confuse anyone. 5t5 and 6t5. Okay. Instead of relates, because I want to start using the actual letter we use. So by theorem 3.31, we can form a partition of A by finding equivalence classes of T. So if we look again to find the equivalence class, in this case, so we've been given the relation. So we look at our X value. So we're going to have, so 4 mod T is equal to, 4 only relates 4. So it's the set containing 4. 5 mod T equals, I want to put it in a more numerical order. So 5 mod T, so 5 relates to 5, 7, and 6. So 5, 6, 7, the set containing 5, 6, 7. And if you notice, that's equal to 6 mod T and 7 mod T. So in terms of our partition, so the partition produced by T is our A mod R. So it's what our mod is. That's also our partition, which is the set containing 4 and the set containing 5, 6, 7. And you'll have some homework problems where you have to work with this. So you want to make sure you understand this example. And actually now will be a good time, because the next thing I'm going to do, I think it's a proof, and I'm pretty much done after that with this section. So the homework for this section, it's not a lot. It's number 2, A through C, 3B, 6, B and C, 8, A, B, and C, and then number 10. And this is, of course, for section 3.3. So I will stop this video and start the last video for this section.